Now let's look at power series. So a power series centered at 0 is a function of the following form, where the ANs are a sequence of complex numbers, Z is a complex number, and we're going to be determining basically when power series converge. So for which complex numbers do they converge? And we've already seen an example of a power series, namely the geometric series. If I have the sum from n equals 0 to infinity of z to the n, we already showed that this converges for z less than 1 in modulus. The first thing we want to point out about power series is that if a power series converges at a particular z0 inside the complex numbers, then it converges for all z with smaller modulus. This will imply that power series always have an open disk of convergence, and it will allow us to talk about something called the radius of convergence, which would be the largest open disk on which the power series converges. This theorem basically follows from our basic necessary condition. So if our power series converges at some z0, then the terms of the power series, an z0 to the n, have to go to 0. Again, that's the basic necessary condition. And if the terms go to 0 in particular, they have to be bounded, say, by some number m. And now I can just directly show that the power series is absolutely convergent for z's with modulus less than the modulus of z0. So you look at the sum of the absolute values of the terms of the power series, and I just kind of rearrange things in here to put the an z naughts, and it looks like I have a small typo here. Okay, we've rearranged it into this, so I have the z naughts, and I have z over z naught to the n. And now this part I can bound by capital M. And then the other part is a geometric series, which I can sum exactly when this part is less than 1, which is my condition that the modulus of z is less than the modulus of z naught. And so you get that it's absolutely convergent in this range. This theorem lets us define something called the radius of convergence. So the radius of convergence of a power series centered at 0 is going to be this number r, which is the supremum of all the moduli of z's for which the power series converges. By the theorem we've just shown, it turns out this is also the supremum of the moduli, and it looks like I have another typo in here. I don't know why I kept writing that. So by the proof of the last theorem, this number r is also equal to the supremum of the moduli of z such that we have absolute convergence. Because whenever we had this series converge, you could take any other point with slightly smaller modulus and you had absolute convergence. So these suprema will be the same. This also says, the theorem also tells you that the series will converge for all z in modulus less than r. Again, that's just because if I stare at the radius of convergence, there has to be a, say, w where the series converges, and then by the theorem you get that the series converges at z. You also get that the series diverges for z in modulus greater than r, because if it did converge for a z greater than r, then that would contradict the definition of radius of convergence as a supremum. We're not going to talk about the behaviors that occur on this circle where the modulus of z equals r, because there's many things that happen there, and it's a subtle question. Notice the radius of convergence can be anything from 0 to infinity, 0 and infinity included, and this is the extended real number infinity, which just means that the supremum of these numbers has no bound. Let's talk about one way to think about the radius of convergence, which is the following theorem that we'll establish, that the exponential rate of growth of the sequence that you use to build the power series is equal to 1 over the radius of convergence. Now, this fact makes it easier to think conceptually of what the radius of convergence is, but let's talk about exactly what it means to say exponential growth rate of a sequence. So take a sequence of complex numbers. It has an exponential growth rate at most the number a if for every b bigger you can bound the sequence by a constant c times the b to the n's. So we're not saying you can do this with a itself, but it does not grow faster than the sequence a to the n. And then we'll say the exponential growth rate of the sequence is the infimum of all of the a's, such that the sequence has exponential growth rate at most a. So you look at all a's for which this holds, and you take the infimum, and that's what we're calling the exponential growth rate. Here are a few other notes about exponential growth rate. So we do allow the exponential growth rate to be infinity if the set over here that we use to define it, to define this infimum, is empty. So if you can't ever bound the sequence by a sequence of powers, then the exponential growth rate is infinity. Notice that for a number to be less than the exponential growth rate means that the sequence actually is bigger than b to the n for infinitely many n. And this is just if this happened for only finitely many n, then that would mean that you had the opposite inequality for all but finitely many n. So you could throw in a constant in here by avoiding those finite, that finite number of n's where it failed. And then you'd get an exponential growth rate that was strictly smaller than our definition of exponential growth rate. It's also worth thinking through the definition that the infimum over here is actually attained by rho, meaning the sequence has exponential growth rate at most rho. So you can always take a number bigger than rho and bound an by powers of that slightly bigger number. And as we already said, 1 over the radius of convergence of the corresponding power series is equal to the exponential growth rate. So here's a theorem which connects the exponential growth rate to radius of convergence and some other quantities. So rho here was the exponential growth rate of our sequence. And the first part of this theorem says you can just calculate it as a lim sup of the ANs to the 1 over n. And it turns out you can calculate this in other ways. So if the ANs are non-zero for n large enough, we get this bound that the lim inf of the ratios is less than or equal to the exponential growth rate, which is less than or equal to the lim sup of the ratios of consecutive terms. And if this limit actually exists, then you can show that the limit of the AN to the 1 over n's exists, and the exponential growth rate can be computed from consecutive ratios. So one thing I want to emphasize is here that A and B are things that you might see in a real analysis course, so we're not going to prove them. You also see this possibly in a calculus course, maybe presented in a slightly different way in terms of the root test and the ratio test for series. And so if this limit exists, here we can get one way to calculate the exponential growth rate. And you can also compute the exponential growth rate without any extra conditions using this limit of roots, or lim sup. The thing here that we're going to actually go through and prove is the fact that the radius of convergence of our power series is equal to 1 over the exponential growth rate. So before we prove item C, let's go through a bunch of examples of actually using A and B and C to tell us what the radius of convergence is of various power series.